All right, let's get started here. Good morning, everyone. So today, the plan is for us to finish the especially the temporal part of the analysis. And then on the second part of the class, I want to talk about quiz 4. There were some very interesting insights from my side to see what is clear, what perhaps is a little bit muddier, and what I need to just like try again, perhaps a different way of just showing you some of these concepts to make sure that you understand them. Okay, so for the, let me just, so for the first part of today's class, we're gonna again finish the spatiotemporal analysis. This is again how my folder looks like. It should still be within the EOMonitor project, so we have not created a new one. So I'm just gonna come here and launch my RProj icon so that our studio environment launches on the side and is focused on this specific project with data and code. So when it launches on your side, you're probably going to be seeing something similar with the usability partial code. That's the one that we're going to be finishing today. If you're not seeing that, again, you can click on that R blue button, go to code, and it should be in this folder here. So you can just launch it through there as well. And so if if you have your outline open, if you don't have it, you can just toggle on and off by clicking on it. But whenever you have it open, you can go to the, I think it's the chunk all maps is the one that we did last time. Yeah, so we finished this one here. So if you want to come to the next chunk, which we don't remember now if we ran, maybe not, but let's just assume we didn't run this. So we want to run everything above this one. So you go to the chunk that has the 3 summary functions and just click on that run all chunks above. And you can keep a look at your green bar. If it goes, like if you didn't leave any errors lingering above, it should run successfully all the way to here. If you want to make sure that it ran successfully, one way that, so the data sets we're going to be using is the SY17, 19, and 20. So if you just like run any of them and print below, you should be seeing what they are as far as having 4,032 rows and having that SY for a standardized yield and the year and the geometry column. Okay, I'm just going to do a quick check. Was someone not able to get to this point successfully? This is what we did last class, so I'm assuming you should all be able to, but just want to check. All right, I don't hear anything. So I left you 3. So if you come down to the next chunk here, I left you 3 summary functions there. So each one of them is for each one of the years, and it's just using that $sign to ask for a summary of only the yield or the standardized yield column. So it's not going to give a summary of all the columns, even though we only have 2. But if you just run like one by one, so the way I do that, you could just run the entire chunk, but I think that gets a little bit more messy. If you want to run just a specific line of code, just have your cursor anywhere in that line and just push Command Return on a Mac or Control Enter on the PC, and it will run just that. So we can just like go one by one here. So in 2017, so remember, standardized yield. What is the unit of that?
Which is the same which we have for you.
It's not possible. Somebody online had a.
It's a relative term, so either it's in percentage or fraction.
Yes. Sorry. Who was that?
Kriti.
Oh, Kriti. Thank you, Kriti. Yeah, that's right. So it is a percentage, right? Because if you remember standardized yield, we standardize by the median and multiply by 100. So this is a percentage, right? So now basically saying that for the standardized yield in 2017, it varied from 25% of the median all the way to 160% of the median. So very large variability for that year. If you run the next one, so for 2019, it varied even more. It varied from about 7% of the median all the way to 161% of the median. And then in 2020 was a little bit less variable, but still variable, going from about 37% of the median to 157% of the median. So we see that now this being in percentages and being standardized by their own year-specific medians, now they're in the same terms that we can really merge them. And even, so in this case here, all 3 years were cotton, even if they were different crops with different ranges of pound per acreage, I guess magnitudes. At this point, they would be comparable, because then you're comparing to the median, you're standardizing that median, whatever that scale of the median would be for different crops, it would be taking that into account. So now they're comparable, right? Okay, so now if you all of the grad students and some of the undergrad students did the assignment 7, which was a reading assignment of the paper that is basically what we're replicating here in code. But you probably saw on that paper how was their approach to get this. How can we get like 3 years of 3 years of data for each one of those years and then combine into one spatial temporal layer, right? So basically, and imagine here we have 3. You may work with farmers that may have 5, 6, 10. Well, hopefully that's not pretty common, but it would be awesome if they had 10 years of yield monitor data that you can use here. So how would you combine all those many different years of yield monitor data into one? So that's what we're going to get here into the spatial temporal stability part of the code. So if you read the paper, you realize that the way they use this, or the way that they summarize these, in our case, 3 years of data into one, was using the coefficient of variation of each one of the pixels over 3 years, and also the yield mean, or the standardized yield mean of each one of the pixels. So those were the 2 pieces of information that we need then to combine these into one. So the first thing that I want to do here, if you come to the next chunk, is we're going to calculate the pixel-based mean and coefficient of variation for each one of, or for all of those years together. So to do that, if you imagine, we have to have one object that has at least 3 columns, where each one of the columns is going to be the standardized yield for a given year, meaning that we have to merge those 3 years first into one data frame. So to do that, we're going to, if you come here in the next chunk, we're going to start with sy_17. We're going to add a pipe. And we did use left joins before. So if you remember, left joins is a function that you use when you have 2 data sets that are different. So let's say you have one that is soil sample and one that is, I don't know, something else from that field, perhaps yield, and somehow they have a column that is the same, right? Well, let me take a simpler example. Perhaps if you do field research, right, and then you go and you collect, you have a plot, let's say you have 40 plots, you have 40 rows in this database. One database, you have plot ID, and then you have yield. The other one, you have plot ID, and you have, let's say, soil phosphorus levels for each one of the plots. How do you merge them together? You have to have one column that is the same and has the same title and same levels in both data sets, and you do a left join. So left join basically merges both the information of yield and soil phosphorus based on that ID that is the same across both data sets. Here, because we're dealing with geospatial data sets, we use a similar concept, but is a little bit different. So the function, instead of being left join, is going to be st_join. Still going to be a join, still a similar concept. The only difference then is, instead of using a common column across both data sets, it's actually going to use the spatial extent of both data sets and merge based on that. So that's what we're doing here. So first thing, we're going to join the sy17 with sy_19. We do have to change a couple of arguments here. So if you add a comma there, I just want to say join equals st underscore equals is the name of a function. You don't have, so you may be prompted by RStudio to have the function st equals. You don't have to have the parentheses there. So just delete the parentheses, just leave the word if you can. And then add a comma, and we're gonna say left equals true is the other argument. So these arguments here just make sure that is doing the correct join based on what we need. If we were to, well, let me just run SY17 first, so you see, right? So it says SY17 has a geometry, SY19 is the same, but it's just called SY19. If we run the SY all at this point, and we print it, we basically end up with the same number of rows of both data sets, which is always something good to check. So sometimes you may do a join, it can be ST join, so a spatial join, or maybe just a left join with a regular data frame. Always check the number of rows of the product that you're creating, in this case, SY all, because sometimes it's not what you expect. And in that case, it's probably something that happened that you should be aware of and change. So always make sure you check that. But here, I mean, it's, the same number of rows of both data sets. So that makes sense. We have the SY17, the geometry coming from that SY17 object. And now we have a new column, SY19. Notice how it did not repeat the geometry column here because it realized that they were matching in space, and that's what the join did. So that's why we only have one geometry here. Okay, so we have 17 and 19 already here. You can add a pipe, hit return, and I'm actually just gonna copy and paste this actually. Yes.
So this st equal, it means it's check the geometry, like the polygons, which are equals, then they join.
Right, is basically, so if you're interested in learning more, so there are a whole bunch of different types of joins for st join because it is spatial. If you're interested in seeing what other options are, you can just do a help on the function st join here in R, and then you can check the argument join. It has a whole explanation. But st equals is basically looking for that equality of, like, it's trying to match equally what polygons are matching within each one of the data frames. So that's what this is doing. The default here, if we did not change this argument, the default is not st equals, and the default option does not give us what we want. So that's why we're changing here. But yeah. Okay, so if you just copy what we just did here with the st join and paste it, the only thing we have to do really is just change SY19 to SY20, because so we're starting with SY17, joining with 19, and then joining with 20. And I mean, if you just delete this last, at least I had on my side a pipe here. If you just delete that and then you run it, just so we can print up until this point, and we print it. So basically now it just added that extra column of SY20 standardized data, right? Which is coming from the SY20 object. Okay, so at this point, we have pretty much joined all the three data sets. That's what we needed to now use these three different columns to do our calculations. So the first thing that, as I was telling you, the goal of this chunk is to calculate the mean standardized yield and the coefficient of variation on a pixel basis. And I just want to make it clear something. I'm saying pixel, and I guess when I thought of this, I was trying to use a word that would be more relatable. But really, pixel is something we talk about when we refer to raster. This is not raster, right? This is a vector file. And these are actually not pixels. There are cells that are polygons, right? So you can kind of think when we did that translation from the grid being a raster, which had pixels, to a grid being a vector, which had polygons, it basically transforms each one of the pixels into a small polygon. Here we have small polygons because a vector is an SF object. I'm using the word pixel just because I thought that would be, easier to relate to, even though now I see how it can be confusing. But anyways, we're working with a vector object here. Okay, so the first thing then, let's calculate the the mean standardized yield on a pixel or a polygon basis. So let's add a pipe there. We're gonna use, so every time we're creating new columns, we use the function mutate. I'm gonna call this mean underscore pixel. Say equals, and then this is basically gonna be, we call the function mean, and we're gonna give it 3 values here. We have to give them within the C. So if you remember, C is for concatenate. So within the C function, we're just gonna say SY17. So these are column names, not object names, right? So SY17, as you can see below, SY19, comma, SY20. So this is what we have to do. And if you make sure you have your parentheses on the right place, make sure you close all of them. You can always scroll like I'm doing here to see that which parentheses you're closing. And then if we run this, let's just run and print it. Okay, so here's something interesting that is going to be a new concept for us when it comes to data wrangling. Every time we use mutate and we create a column that is based on a summarizing function. So if you think of it, mean, ST, CV, minimum, maximum, median, those are all summarizing functions, right? So when you use a summarizing function inside a mutate, what it does is it summarizes over the entire data frame. So all the 4,032 rows, and it gives you one value, the same value for all cells. So if we were to just browse here, everything under mean pixel is 97.45 because that's basically the average of SY17, 19, and 20. That is not what we want, right? We want the average for each one of the cells. So let's say for the first cell, I want the average between 91, 94, and 92. That's the value I want here, which is going to be different to the second row and for the third row and so on. To fix this, we have to, before we get to this mutate, we have to call another function just to set up the way we want to conduct these means calculations. It's a function called Rowwise. So if you just write Rowwise and then yes,
I'm having an error running that previous chunk. It says error in mean object SY17 not found. I don't have an underscore or anything. I don't exactly know why. I can't find, or it's not running.
So let's say if you're looking at my code, the way that I would troubleshoot that
Sorry, Professor.
is I would
I think I can help. I got the same error. I think he copied SY all, the first line as well, and we were not supposed to copy that.
No, I didn't copy SY all.
okay.
All right, then it's something else. Sorry.
Thanks. Who was it? Was that Umar?
Yes.
Yeah, okay. Thanks, Umar. Thanks for the help. Okay, so the way that I would try to troubleshoot that is I would stop the flow right at this pipe here. Right. So if I just run everything above, it's going to stop here because now the pipe is inactive. So if I run that, when you do that, does that
run?
Say that again?
It runs when I turn the pipe off. It's just when I get to that, it says.
Okay, so I would stop the pipe there and run until this point, right? So anywhere in here, I have my cursor and I hit command return, and then I print it. So when you print it, do you see SY17, SY19, and SY20 there?
There's the issues in this mutate, it's in the mean.
So I didn't print that, right?
And it should be mean pixel. And you can see. Alright. Which have is. Hey, you don't have your underscores in your SYs.
Oh, we weren't supposed to have them there.
No, you need, yeah, that's what you need.
Yeah, remember that
Oh,
like the data set
Underscore,
have
right,
underscore, or
yeah.
the objects have underscore, the columns do not.
But so I need them here. I don't have it there.
Did that work?
I'm sorry, Dr. Bassett. I don't know, no, I mean, I'm running all but, and then printing.
So make sure again that you're like, your data sets coming in have the underscore, but when you're doing the mean of the columns do not have underscore.
I don't have underscores there, no, sir.
Okay. Make sure you
And
have
to my
like,
knowledge, it's the same everything you've got up there. I mean, I mean,
if you have like,
it's running,
if you have some issue in the code, sometimes it pops, it shows like an X right next to the line of where the code is possibly wrong. So I would use that as a guide as
Yes.
well. Sometimes you may be forgetting a comma, or maybe like your parentheses are not closing and matching properly, something like that.
Doug Messers.
Yes.
I had the same issue earlier when we were running the summary chunks, like it was telling me SY17 couldn't be found.
Okay,
So I had to go all the way back to the original chunk where we assigned SY_17. And there's a part in there where where I had written SY equals SY comma geometry, but I had to change that to SY17 equals SY comma
Yes.
geometry.
thanks, doctor. I think that's probably it. So let's, Austin, were you able to hear?
could you repeat it? I could hear a little bit.
Yeah, so what could happen is if you come on your outline here and you go back to the data import, well, let's see, no, to the SY17 chunk, if you go to that one,
You probably have an underscore there.
make sure
Oh, yeah,
that you have on the select, make sure that you're also renaming that SY to SY17 at this point.
I did have an underscore right there. That might be it.
Yeah, so you don't want to have the underscore here. I mean, not, because here we're renaming the column name, not the data set.
That was it. I got it.
Okay, awesome. Thanks, Austin.
Thank you.
Yeah. All right, everyone else, was good. I mean, if anyone has any issues, you're always free to speak up and we can troubleshoot it. All right, so if we come back to our SY all object, I'm just going to uncomment the pipe, and I'm gonna uncomment my Rowwise as well, just so we let it go through. So the Rowwise function, basically, so the default behavior of mutate is to do that. If you're using a summarizing function like mean inside a mutate, you will summarize for the entire data set, calculate one value only, repeat that value all the way down. For us to change that default behavior, we just have to add this function called Rowwise before we do that mutate. And if you run it now and you print it, you're going to realize that now each value of mean pixel is different and is actually being calculated in a Rowwise manner, which is what we want. Okay, so we have the mean calculated for each one of the pixels, or perhaps the polygons would be a better word to use. Let's go ahead and calculate so if you remember, we calculated CV, coefficient variation, before, but there's no function to do that in R, right? So we first have to calculate the standard deviation, and then from that, use that in the means, calculate the coefficient of variation. So let's do, yes.
So I don't know, maybe because when I created separated the GeoJSON file,
Mhm.
I round up, I use the round, but getting different values.
Different values for the mean pixel?
Yeah.
We can check that later. I mean, yeah, I guess for now, as long as you can follow what we're doing, even if the values are a little bit different, but we can come back to that later and see. Okay, so let's go ahead and calculate the standard deviation first. So we're gonna use a mutate again. I want to call this column SD underscore pixel. So now pretty much instead of calling the mean, we're going to call a function called SD. And we're going to also use the C function here, so the concatenate function, just to give again the same column name. So SY17, comma, SY20, or sorry, SY19, comma, SY20. So remember, these are column names and not the object names, right? So if you run up until this point and you print it, now we have an SD pixel column that has the standard deviation for each one of the cells. And again, it is doing on a row by row basis because we call Rowwise. So that basically is carrying over to anything that comes after it. So that's why the SD pixel is also specific for each one of the rows. And then lastly, we have everything we needed to calculate the coefficient of variation, which if you recall is just dividing as the standard deviation by the mean and multiplying by 100. So that's what we're going to do next here in the next chunk. So we add a pipe. Let's use a mutate function. I want to call this this new column here as CV underscore pixel equals, and that is basically just doing the, so I want to open and close another parentheses here, just so we have the division inside of the parentheses, then multiply by 100 outside of it. So we're going to do the SD underscore pixel divided by the mean underscore pixel. So again, dividing standard deviation by the mean and then multiplying that by 100. So you can have that on your code. If we run this and we print it, we have now our CV. And CV, if you recall, so the coefficient of variation is a percentage, right? So that's the unit of the CV. And in the case here, the mean pixel is also a percentage because it's standardized yield, right? So it's all being relativized at this point. Okay, so we basically calculated the columns we needed to do the spatiotemporal classification. If you come to the next chunk here, I just want to just explore a little bit what these values are. So if you just come here, I left you the chunk already, the summary for, so first looking at the mean pixel values, if you just run that. So when you take, so imagine that for a given pixel on that field, right, we took 3 years of data and we calculated an average. So now we just one value per pixel, not 3 anymore. So the mean of the pixels vary from 34% of the standardized median to 137% of the standardized median. That's how the average standardized yield on a pixel basis varied in this field.
3 years average.
A 3-year average, yeah.
On the last line,
Say that again.
the last line is like,
Oh, you
Previous portion.
need to type this, is that what you're saying?
I don't know, like when we run to get the mutate CV pixel.
Mm-hmm.
So,
Oh, you want to catch up? Is that what you're saying? Okay.
yeah. I think I found the problem.
You found? What was it?
There's a place instead of putting, yeah, like 20. You should like put 19.
Ah, okay, okay. Yeah. Was that in this script or in a previous script? Okay. Yeah. Yeah, it's not working? Sorry, for everyone online, we're just troubleshooting here quickly something. So make sure you have on the mean pixel and SD pixel, make sure you have the C function inside of the mean and SD functions. And make sure your parentheses are matching as well. So if you have like less than or more than needed parentheses, you're probably going to have an X showing on your line number, showing like there's something wrong here. Is it not working? Okay, let me just come here quickly.
So when you run, what happens?
Well, if you run all the chunk, does that give you an error? Like if you just play the chunk, let's see.
You got I think I wrote somewhere pixels instead of pixel.
Oh, yeah. Sometimes that can be. All right, let's continue here. So we have the three pieces of information that we need to calculate the spatiotemporal classification. However, before we do that, let's just explore a little bit what we just did here. So look at some summaries and perhaps some plots as well. So if we just asked for a summary. I know this is going to be a little confusing because we're summarizing now all the entire column mean pixel, which was in itself a summary of 3 years. So bear with me if that's confusing. But so we saw that on a pixel basis, on a polygon basis, the small polygon cell size for this field, the average standardized yield across 3 years vary from 34% to 137% of the median. If we look now at the summary of the coefficient of variation on a pixel basis, we see that on a pixel basis, the coefficient of variation varied from 0.24%, so very little, almost nothing, right? All the way to 77% of variation, which is a lot of variation, if we think of it. And this variation, I know like we're doing a whole bunch of steps that may become a little bit more difficult to interpret, but 77% coefficient of variation on top of standardized yield across 3 years, right? So this is what this value is telling us. Okay, so if you come down to the next chunk, I just want to make a density plot. So you're already familiar with this. We're starting with the ggplot, calling the data set that we're going to use, which is the one we just created above. And I want to have on the x-axis the mean underscore pixel column, because I want to see a density plot of the mean pixel. And then I'm adding a geom density, which adds that line, that kind of like normal distribution line, and then geom rug to add the points below it. So we see here that, again, for this data set, we have the mean standardized yields varying on a pixel basis, varying from 30 to, I don't know, 120. Well, we saw that above 137, I guess, was the value. But most of the values are really around, let's see, this is 90, this is here 15, so 80 or 105. So most of the values are around 105% of the median, right? So they're pretty consistent, but we do have some outliers that we're going to be looking into. And then lastly, I just want to make a plot here, density plot of the CV underscore pixel for us to look. So if you go to the next chunk, you just replace those 3 dots by CV pixel. And just looking at that, we see that most of the points are around perhaps, I don't know, 7% CV, which is not bad, right? But then we have this long tail here because we have a lot of data points that have very, very large variability, right? So if you think of it in a field, if you have points that have such a large variability just across 3 years, that could be certainly related to weather patterns, right? I mean, that's what's mostly changing from 1 year to the next, but also how weather patterns interact with the field itself. So perhaps with, elevation, or maybe you have dips in the field, or maybe you have, different slopes, or just things of that sort. So it's weather, but also how that interacts with the field itself. Okay, so we did a very quick EDA, exploratory data analysis here, just to see how the data look like. The next thing I want to do is just create a map of the standardized mean that so that was the mean pixel column. And okay, so now this is something that came up on the quiz, and I just want to use this opportunity to go through that concept again. So the object that we have is sy underscore all, right? So this is the one that we're going to use to create this map that we're using here. If I print this, just to remind you, this is an SF object, simple feature collection. So we know we could have used also the function class if you want to know what type object that is. So class is type SF. So it is an SF object, right? So if I tell you as one of the questions of the quiz that I want to create a map or a plot where I want to use this object here, which is, I just told you is an SF object. Before we really get into the coding here, what geom are we going to need? Emma, what do you think? Yes, that's exactly it. Because this is an SF object, right? So if we want to make a map of an SF object, we need GeomSF. So if we just, I'm just going to delete that from there because that was just to print it below here so you could see. So if we come here to the next chunk, so we're starting with ggplot already. I left you that part, and we're going to save. So whatever we develop here, we want to save that as an object called sy all mean, so we can call this plot later as well. So that's why we're saving that to an object. So add a plus after that ggplot. We're going to use geom_sf again because this is an SF object. So the first argument we give it is the data, right? So the data coming in is sy_all. That's the one that we just did above with all 3 years together. I would just want to give some spaces here to break the code, but the next thing that we want to give it is the AES function. Well, so you know what? You can leave it as is on your side. I just want to show you something here. Another thing that relates to what we did on the quiz, or a question I asked on the quiz. So if I just run this and I printed, this is what it gives me, right? So it doesn't give me much information as far as like, it's not coloring anything by anything else. If I just at this point here come and say color equals, so we want to do the mean, that would be the mean underscore pixel, right? So if I just do that here, it's not going to work. However, I could, instead of calling a column name, I could have said color equals, let's say, red. And that would have worked. It was just going to change everything to the same color. What am I missing if I want? So every time you want to map a plot aesthetics, so it could be color, fill, transparency, point size, whatever it is. When you want to map that to a column in the data, and you want them to go together instead of just applying one value for everything like I'm doing here, what do we need? What am I missing here?
Aesthetics.
Yes, aesthetics function. So we have to call AES here. So now we can start coding again. We have to call aesthetics here and say fill equals mean underscore pixel. If you remember, I did say here color equals mean pixel outside of the AES function, and it gave me an error because it has to go inside AES if we're mapping an aesthetics to a column. And then if you come outside of the AES function, you just add a comma there. Now let's just say color equals NA. So again, we're working with polygons. So color in this case means the outline of the polygon. I just want no color there because so it doesn't become cluttered when we see it. I just want the fill, which is the inside color, to be changed according to mean pixel. So if we just run that and we print it, this is what we get. And I just want to do a few modifications here, as you're probably already expecting. So I want to change this color scheme here to be colorblind safe, right? So we add a plus, we say scale underscore fill underscore viridies. I want to use viridies B for bend. I want to change a couple of things inside of this function. I want to change the color choice or palette choice to C, and this has to be uppercase just in case you, so this ranges from A to F, I think, and they all have different color schemes that are all color friendly. I want to say C and it has to be uppercase. So if we just run that and you print it, it changed to this type of map or this type of color scheme. And it did come up with some automatic breaks for us there that it calculated on itself. I do want to change that a little bit. So I want to have if you come back to scale field radius B, add a comma after the option equals C. It has an argument called breaks. That is how we define which breaks we want. I want to just have two breaks. So I want to give the C function because I'm giving two values, and I want to have a break at 80 and a break at 120. So a break at 80% and another one at 120%. That's my goal here. So if I run that and I print it, this is how it looks like. If you read the paper and if you answer the assignment, you may already be imagining why I chose those specific breaks. But if it didn't, that's coming up next. All right. So again, this is the mean standardized yield over 3 years on a pixel by pixel basis, right? So we see that the pixels that were yielding the highest, at least when we look at the mean over 3 years, were the yellow ones. So lower here, we do see that pattern that we had already saw on the individual years, that the lowest yielding points were coming from this eastern side of the field. And also we kind of see a little bit here that those eroded fingers coming outside as well. And then everything else is in this like intermediate yield level, at least as a percentage of the median, right? So again, these are percentages of the median. Okay, so next thing I want to do here is basically the same map, but for CV, because we just did mean pixel at this point. I want to look at the CV pixel next. I left you almost all the code because we just did that above. We just have to change a couple things here. So on the field, you know, if you've been following, we would change the 3 dots to CV underscore pixel. That's what I want to plot here. And then we're also going to have a different value under the breaks. So the breaks here, I want to change that to just a single value, which is basically going to create 2 classes. So that single value is going to be equals to 30. If you run this and you print it, this is what happens. And again, why 30? You probably know already if you read the paper, and if you did not, you're going to learn that in a second here. But we see here that pixels that had more variability, in this case, more variability being greater than 30%, are also, you know, some of them are close to that eastern boundary. And we see some other kind of like loners across the field as well in different places.
Hey, quick question, Doc.
Yes.
I read the same thing, and mine's blue and yellow instead of like purple and salmon colored. So I don't know why, if that means anything.
You mean just the CV pixel or the first one as well?
My second one, the most recent one, is blue and yellow.
Mine were both different colors, so.
There's Mac colors. Oh, then Mac and.
Oh,
So we have some
different.
conversation on. So what were you guys?
Difference between Mac and Windows.
Oh, okay.
Results are same, just color are different.
Okay. So what I'm hearing here is probably a difference between Mac and Windows. So I'm on a Mac. If you're on a Windows, that may be different, even though that's new to me. I didn't know that they look different across different OSs. But that may
No,
be
I'm running Mac also.
Sorry, say that again.
I'm running Mac also, and mine's blue and yellow on the second one that we just did.
Okay. Interesting. And you have,
I mean, it doesn't matter. That's fine. I was just wanted to let you know.
yeah, no,
And
that's
me and Austin Windows and ours are 2 different colors on the first one.
okay. Well, that is very interesting. I was not expecting that. Yeah, I mean, you know, since it's just visualization, I guess we don't have to worry about it, but definitely something numerical, you know, something numerical comes up as far as a difference between different people, that's when we have to worry. But yeah, that's kind of interesting. I didn't know that. Not sure what's going on there. All right, well, thanks for bringing up, and because it seems like here in Athens we also had differences, and so I'm not sure what's going on there. Okay, so next thing I want to do here is I just want to combine these two maps side by side because since we're using both of them to create the rules of how we're going to classify each pixel for spatial temporal, I just want to combine them together. So if you, that's why also I save them to an object, right? So the first map I saved to an object called sy all mean. So I'm just copying that and pasting that below here. And then I'm going to add a plus here. And the second map that we created was the sy all cv. So if you, let me just do something quickly here. So we did load the package Patchwork on a previous chunk. So this, what we're doing now should work. Because so again, if you don't have the package Patchwork loaded, this plus is interpreted as coming from ggplot2, which ggplot2 does not know how to combine two ggplot objects. However, if you do load the package Patchwork, which we already did above, and you run this, that plus understands that then there are two ggplot objects and it should come, it should use the plus from package Patchwork, which basically does this for us. Oh, and now that I noticed, I think I actually forgot one point of the mean pixel plot. So we can just go ahead and fix. Just a very quick fix is just that, you know, after, so I just came to the mean map chunk again, where we created the sy all mean. We just want to add a plus and change this to theme underscore map. I just forgot to do this when we ran the code the first time. So make sure you run it after you add it so that that change is incorporated. And if you print it below, you should now see this, right? So before we had the X and Y coordinates and it was like a grayish background. So theme map removes that and makes it cleaner, I guess, for a map. So then if you come back again on the both maps chunk and you run that, they should look more similar like they are now. And again, if you want to export a figure, a static figure, we use GGSave. So I left you the code already. We're basically exporting this to the output folder. I'm calling this sytempstability.png, and I just gave it width and height. So if we just run that, the GGSave, and if you come here on your output folder, you should now see sytempstability, and it should be the exact map that we just created. So again, this is how you would export a map if you want to use in anywhere else outside R. Yes, Bo?
One or two things. Can you scroll back up to the map? Missed that last.
Yeah, so I just added a plus and then added the theme map at the end.
And also, I couldn't get mine to say. It can't say.
On the, so you mean like here when you GGSave doesn't work?
Yeah, it wasn't running fast at first. It means plus the C. Not running fast.
So if you just like select those two there and you run them, like don't play the whole chunk, just run the maps, does it come up? Like, do you see the two maps side by side? Or is there error there?
It says error in GT_.
Okay. So that's because, so try to do this. So so Bo here is having an issue that is not, this is not running, the combining both maps. Try to do a library Patchwork up here, just so we load that package. It should have been already loaded above, but for some reason, if that was not the case, you can just load that here and then run the map. And now it should join them. Awesome. Yep. And also just to remind you here, one of the reasons why we use our studio projects is because our relative paths are really easy to write them down whenever we're importing or exporting something, right? So here, again, if maybe you tried to GGSave and didn't work, you're just gonna make sure that, you know, in my case, if I go to my main folder of my project, I have code data and output all lowercase. If you have maybe your output folder as uppercase O, you know, maybe that's a difference. And maybe if for some reason you don't have the same structure here, you would have to adapt to your case as well, as far as the folder structure when you're outputting. But that's, yeah, that was it. Okay, so let's get to the classification. If you read the paper, you're already familiar with this. If you did not, because you were not required to, just want to quickly run through the thought process behind this. So the paper that I share for the assignment 7 is basically a protocol that we're following here. We're just applying that to our own data. And what they recommend is if a pixel has a coefficient of variation that's greater than 30%, then that pixel is classified as unstable. I'm calling it unstable. I think they were calling something else similar to this, but still or inconsistent, I think they were calling, but it's basically unstable, right? Because you have a high CV, meaning that in 1 year, the same place of the field may low very high, and the other may yield very low, and it's just unstable pixel. Now, if a pixel has a CV less than 30%, then we break that down into 3 classes. So if it is less than 30%, then it is stable, or is going to be, it doesn't vary as much over time. And so if the CV is less than 30% and the standardized yield is more than 120%, then that's classified as a high stable. If again, CV is less than 30, as we just said, but the standardized yield is between 80 and 120% of the median, then it's classified as medium stable. And if CV is less than 30% and the mean standardized yield is less than 80% of the median, then it's classified as low stable. And remember that when I say yield is less than or equal to 80%, 120%, and so on, that is the average over 3 years. It's not year specific anymore. It's the average of the pixel over 3 years. And same for the CV as well. Okay, so let's now translate what we just said in words into code. So if you come on the next chunk here, we're going to use, we're going to start off with the data set that we have. That's sy_all. We're going to add a pipe here. So the goal is to create a column that is going to basically say, have one of these 4 values for each one of the rows, where the 4 values are going to be unstable, high stable, medium stable, low stable. So since we're creating a column, we're going to use a function mutate. I want to call this new column st class for spatiotemporal classification, short for that. And okay, let me ask you something code related. If I'm telling you we have 4 conditions, right, that we want to classify pixels into 4 different levels that have different conditions, each one of them, which function do I need here next?
Case Wayne.
Yes, case when. Who was that?
Saker.
Okay, perfect. Thanks.
Saker.
Thanks, Saker. Awesome, that's exactly it. So we use function case when, right? Because then that allows us to give conditions based on columns that we have, and then create a new column based on those values. So, okay, let me ask someone else's help here. How would you translate? So I just want to print sy_all below here, so we see again, right? So we have sy17, 19, 20. We have mean pixel, and we have CV pixel. And ST, but we're not going to use ST. I mean, we're just going to use mean pixel and CV pixel to tell the truth. But how would you translate this first condition into code? Like, what would you type? Well, let me do this. Let me start the first one just to remind you how case when works, and then I'll ask different people to help me with the following ones. So the first one is, if we look here, if a pixel has a CV more than 30%, then it's classified as unstable. The way that we would do that is just to remind you the column name is CV pixel. So we say if, I mean, we don't have to say if, but I'm just saying words here. CV pixel greater than 30%, then the way we say then is using tilde, then the ST class receives the value of open and close quotation marks, unstable. Okay, so that's how I translated that first sentence into code. Now, to give more conditions, we just add a comma and keep adding conditions. So let me ask someone here, how would you write the second condition in code? It's going to be a little more complicated because now we're using both the CV and the mean pixel, but just think about that for a moment. How would you do that? Okay, so Peter is saying CV pixel less than 30, right? And mean pixel greater than, okay. Then, so tilde, pi stable, right? That's perfect. And I just want to show you something here. So when I was preparing this class on my side, I was just using less than, greater than. But then there was a few cases that the values were exactly 120. And because my condition doesn't have equality anywhere, then it didn't know what to do and it gave me an NA. So to avoid that, to say, so right now we're just saying less than or more than. If we want to say equals or greater than or equals or less than, we just add an equal sign after the greater than or lower than. That's how we would do. And this perhaps is one of the reasons why when we want to say equality, like this equals that, we use double equal sign, because it's kind of a placeholder for when we want to have an equal, but also another subcondition, I guess.
Dr. Bastos,
Yes.
you've said before, but could you please tell me again what the tilde function represents?
So the tilde is just a programming way of saying then. Right, so if CV pixel is greater than 30, then ST class is named unstable.
Okay, thank you.
Yeah. Okay, so let me ask someone else now. This is probably the most complex one, even though it's not super complex, but it's the most complex of the ones that we're doing here. How would you specify the third condition? So we did this one already. If CV greater than 30, then unstable. We did the second one, which CV lower than 30 and standardized mean is greater than 120, then high stable. Now the median stable is the most perhaps complex of the ones we're doing to turn into code, even though it's not terrible, but so maybe, you know, if a couple people, different people can help me here just to think through this. Tyner, what do you think?
So you start out similar to the before you see pixel greater than 30.
Less than, greater than 80, right? Yeah. So yeah, so we just add, so if we just stop here, then it would basically reclassify, including the ones that we already classified as high stable, right? Because greater than 80 includes greater than 120. So we have to put the upper limit on that classification. So we have to say, and so, well, sorry for those online. So Tyner was saying we start off the same way as the one before. So a CV pixel less than 30. And now we say equal and mean pixel greater than 80, and also have to say another n to give the upper limit of that mean pixel. So mean pixel less than 120. And I guess in this case, well, okay, so that's the condition, right? And then we say tilde to say then, and then we open close quotation marks and say medium dash stable.
We don't need the equal sign.
Yes, we do. So we're going to need an equal sign here on the 80. So we say greater than equal 80. Yeah. All right. So if you want to make sure you got your like greater than, equal than, tildes, commas, all that in the right place, we can just run up, and even though it's not complete yet, but if you run this, if it doesn't give you any errors, then you're, oh, you know what? This one here. So this one, I didn't have to add one because there was no single value that was exactly equal to 30. Yeah, and you know what, I asked you all to run this, and I just remember that this chunk takes a little bit of time to run. Maybe I should not have asked you to run it. But, I mean, at least not yet, right, because we haven't finished it. But I'm just gonna wait on my side here, just gonna take, I mean, on my side, it maybe takes, I don't know, perhaps a little bit close to a minute. But let's just, yeah, I'm just gonna wait for that on my side. And I think it'll probably take a little time on your sides as well. No, it was fast. Huh, okay. Is anyone else like, does this take a little longer on anyone else's side? Yeah, so maybe it's just me for some reason. Okay, well, if that's the case, I'm going to just like abort pretty much the running and just continue. Okay. So let's give it, if you add a comma at the end here, let's just give the last condition that we need here, and then we can all run, even if it takes a little longer. Okay, so the last condition we have is this one here. I want to ask someone else now to help me. That it should be pretty straightforward at this point since we already did all the others. But let me see here who has not said much today. Anish, can you help me here with the last condition? So how we will write this one?
Yeah, so CV pixel is less than 30
Mm-hmm.
and main pixel
Mm-hmm. So this is the condition that we're doing.
main pixel
Can you repeat?
less than 80.
Less than 80. Perfect. Okay.
And then that sign,
Mm-hmm.
so we call it and then quotation lowest stable.
Perfect. Awesome. Thanks, Anish. All right, that's it. So let's do this. So this is, you know, again, if you have all of your commas and parentheses right, you should run without problems. I know on my side, for some reason, it takes maybe a minute to run. So I'm going to run this, and while it runs, I guess we have to basically wait for this to run to get to the next part of the script. So I guess I'm just gonna have to wait. If anyone else is also like taking longer, whenever mine finishes running, and if yours hasn't finished running yet, feel free to let me know, and we can hold on another moment as well. So while this is going on, I just want to tell you that, so I finished grading, I guess the two things I haven't graded yet are the mini project and assignment 7 for those who submitted yesterday. I did grade the quiz, and I learned a few things about that maybe I should be more clear, that we're gonna go through like after we finish this exercise today. So yeah, I guess we're just gonna do that in a moment here when we finish this.
Dr. Bastos,
Mm-hmm.
so in where we did mean pixel is greater than or equal to 80 and mean pixel is less than 120, can we do mean pixel is equal to 80 colon 120? 80 to 120 to generate something like that.
You mean like if we were to say equal, is that what you're saying?
Yeah, if we do mean pixel is equal to 80 and then colon and then 120, so will that get us through 80 to 120 data?
No, so every time we use equal, that basically means exactly equal to that. So if you say like mean pixel equals 80 and equals 120, that's only going to give you the pixels that have exactly, well, I mean, I guess that's not even possible to tell the truth. Because, you know, mean pixel is one column only, and it cannot be equal to two different values, right? So I don't think it would even give you anything back. I mean, you know, you're welcome to play around with these on your side, and especially if you try to apply these concepts to different, you know, situations like your own research. But equals is going to be basically equality. So perhaps an easier example to explore your question is if we were to say CV pixel equals 30, what that would do is take any pixel that where CV pixel was exactly equal to 30 and classify that as unstable. However, if it was 30.1, that was already not equals to 30 anymore, and that would not receive that classification. So equals is pretty like, it has to be exactly equal to whatever you're saying, and greater than and lower than gives you that range flexibility, right? Of specifying a lower or upper limit and then being from that point on. All right, so I finished running on my side. Is anyone else still waiting?
Mine ran, but it's got an NA where it's supposed to have a medium stable. So all my medium stables come up as like grayed out NA. And my code is the same as everybody else's here in Tifton, but it's not.
Okay.
Thank you.
And it's just for the medium?
Yes, sir.
Okay, that is kind of weird. So let's troubleshoot that perhaps after class, because I'm gonna need to look into your code and see what's going on. If that's okay. I mean, you're still gonna be able to code. It's just not gonna look exactly like mine or everyone else's, but we can get to that after class. Is that okay?
Yes, sir.
Okay, all right. So if now, you know, I just printed below here this object we created now. So if you just scroll to the right, you're gonna see this column called ST class, where each one of the values now is one of the four that we coded above, right? So if there's a whole bunch of medium stable, I see a low stable on page 5, then there's some more afterwards. But we can really see now how we went from taking into account, it's really like, if you think about it, this classification is basically based on the columns. If you think all the way back, it's based on the columns SY17, 19, and 20, because we use them to calculate mean pixel and CV pixel. And then finally, it takes into account those mean and CV to go from a numerical column now to a categorical or character column, right? So now if we were to map this, the pixel values would not be numbers anymore. There would be classes, the 4 classes that we created. So let's go ahead and actually plot it so we can see that on a map. So if you come to the next chunk, I left you the ggplot call already. You just add a plus. We're gonna use a geom_sf. As always, the first thing that we give it is the data. So we say data equals this object that we just had above, sy all class. Now I want the fill of the polygons to be according to the ST class classification that we just created. So add a comma. We're gonna have to use the function AES. If you recall, we just had the conversation previously. We're gonna say fill equals ST class. You get outside of the AES, add a comma, and I just want to say color equals NA, so we suppress the outline of the polygons. Again, I want to change add a plus and change the color scale, so I want to use the scale underscore fill underscore Virides. And in this case, I want to use Virides D, and D stands for discrete. So B and C are for continuous variables, right? So C is for continuous and B is for bins. So this creates bins of a continuous variable. And Virides D is for discrete, which, because now we have discrete classes and not numerical numbers or numerical values anymore. And again, I just want to say option equals uppercase C, even if that looks different for different people. And then finally add a plus and change the theme to theme underscore map to make things cleaner. So I do want to leave the code up there, but I also want to scroll down a little. So we see, this is what we have going on here in this field. And this is our spatial temporal classification for this field for 3 different years. Okay, so what do we see here? Like, what is the major class inside this field? Medium stable, right? So we see medium stable, which is in my side at least, is the orange color, being the most predominant in this field. Which one is perhaps the least predominant? Trip, what you think?
Right, stable.
High stable, right? Yeah, I agree. I think high stable is probably the least predominant as well. And then finally, you know, if we're really, one thing that we're going to get to in this class is the unstable areas. So the unstable areas are the yellow points in my map. And those are really interesting to, especially for a management perspective, right? So imagine that this is your producer, you're working with them, and you say, look, I know that like in the dark blue parts of your field, you pretty consistently year in, year out to get high yields, given the yield potential of that year. Those areas give you high yields pretty consistently. So maybe we can invest more in those parts, which in this field here is not a major part of the field, but it could be, right? Because this is just one example. On the other side, on your low stable, so the low stable are the purple on my map, you pretty consistently yield less. So maybe you can think of applying less resources there, less inputs, and cut your cost because you're not going to get much yield out of it anyways. However, what do you do about these unstable areas? Because the unstable means that maybe this year you got high yields, but last year maybe it was the lowest part of the field, lowest yielding part of the field. What do you do about an area that you don't know how that's going to behave from year to year, right? So that's something that's kind of interesting to think of, like, how do you even manage that? So it's just something that we're going to address at some point, but not today. Yeah.
I read the same code and my legend is like putting into the map.
Okay. I think it could be because maybe like, let's see. Yeah, I'm not sure. Yeah, maybe that's why, like, if you just, but you know, one thing to of course, like when you were just visualizing, we do want our legend to not be overlapping with the map. But one thing to keep in mind is, like, if you were to export this, yeah, you would actually check the PNG that you're exporting and not here, because as you saw, this window here, like as you know, yeah, it's adjustable, but the PNG, like if we're really exporting to a paper or something, you want to check the actual PNG file and change the width and height of the GG save to change the PNG itself. Okay, so you know what, the next thing that I just want to explore here is I want to know what proportion of this field is covered by each one of these classes. Okay, so we can come here to our next chunk. So this, I left you, this is the object that we created with the classification. So we're not creating a new object, we're just starting with this one. So we're gonna, to be able to know, I guess let me see, I don't think we did this yet in the class. So I guess we'll just walk through step by step. So we're starting with that data set. I want to basically know of the 4 classes under ST class, how many observations there were within this field, right? So we come here, we add a pipe. We're going to do a group by. And we say ST class inside of the group by, because now I want to create groups where each group is going to be one of the ST class levels, all the 4 that we created. And then we had a pipe here, and R or dplyr has this function called tally. So if you run that, it's basically gonna give you a tally of how many observations you had classified as each one of those classes, and it gives you that answer in a column that it calls lowercase n. So this is the actual number of polygons or pixels within each one of the classes. It's not proportion yet. Right? So how would you calculate proportion out of this?
Divide everything by total,
Everything by how much?
like high stable divided by total number of like pixels or column.
Yes, exactly it. So we basically have to divide each one of these values by the total number of rows, which was 4032, right? If we just print the original one, 4032. So let's just go ahead and do that. So we basically add a pipe. We're going to use a mutate. I want to call this prop for proportion, say equals to, and then I open and close another parentheses there just because I want to do a division first and then a multiplication. So the division is going to be n, which is this column that tally gives us, divided by 4032. And 4032 is the row, the number of rows that SY all class had. So I do that division and then I just multiply by 100 to get a percentage. Right, so we see here now we have this new column called prop, and as we visually inspected, right, the medium stable has about 81% of the area covered under medium stable. The unstable, the high stable, which we thought visually was the one that had the least points, is actually true, is just like 3.6% of the area is under high stable, which I guess is, you know, perhaps not what we would wish that a field would be. And then we see 11% or about 12% under low stable and 4% under unstable, but definitely medium stable is the most predominant here. Okay, so the last thing that we're going to do here is export this layer, as this is going to be the layer that we're going to be using for the following, or not the immediate following, but for one of the upcoming exercises. Okay, so let me ask for, oops, the object name is SY all class. So SY all class is an SF, as we know. If I want to export this as a geospatial data set, right? So either as a shapefile or maybe GeoJSON or KML, KMX, anything like that. What is one of the functions that we can use for that? And I mean, in class, we only saw one, but there are more than one. But in class, we use only one for that. What function is that? Write underscore SF. Yes, thanks, Bo. So let's start with that. We come here and we do write underscore SF, open and close quotation marks. The first thing that we, or parentheses, sorry. First thing we give it is the object name. So that's SY underscore all underscore class. Next thing we give it is where we want to save it and what name we want to give it. So I just added a comma, open and close quotation marks. In my case, I need to get outside of the code folder, which is where this script is, / I want to get inside of the data folder. So I'm exporting this into data and not into output because we're still using as data in the coming exercise. So that's why. And then I want to call this SY underscore all dot GeoJSON. Right, so remember that on this piece of the code here, we give the path, but we also give it a name and the extension all in the same line. And then, as we already talked about, add a comma there, and we want to change this argument called delete underscore DSN to be equals true. The default is false, and that appends rather than overwrite, and we want to override in case we happen to run this piece of code twice or more. So if you run that and if you don't have any errors here, you know, again, how do you check if that worked? You can come on the side here, click on the R below button to come to the main folder of the project, go inside the data folder, which is where you just export this into, and you should see an sy underscore all.geojson file right there. Right, so we exported it, all good. Okay, and just a quick summary here before we finish. So in this exercise, we imported 3 years of interpolated of, so let's just like try to make the connections, right? So 3 years of wrangled clean interpolated EO data for 3 different years. We standardized them by using the median of that year to create these spatial stability classes. And then we calculated on a pixel basis, the mean of that pixel and the CV of that pixel, and then use those 2 columns to then create 4 classes of stability. And now is our the last thing that we did here, and exported that layer as well, so we can use later. All right, any questions about the topic, the code, what we did today? Okay, I don't hear anything. So we can basically, if go ahead and we can just close this, I guess, if you want to on your side, because we're not going to be coding anymore. And I guess let me just stop the recording as well and start a new one so we have it separated.